we have something called SQL Server hash partitioning. We can use table partitioning function, the functionality for splitting the primary key inserts. For example, let us say you have a table. Okay, you have a table. The table is not a very huge table. Okay, but the thing is, you are inserting, let us say, 10,000 records per second. Okay, 10,000 records per second, very high writes. Okay, so in certain scenarios you might get page latch. For example, you have a table and the table has column ID. This ID is you have an identity defined on this ID column. Let us say this is orders table. Okay, and orders table, you have order ID as primary key, and the primary key is identity column. Okay, and you are inserting 10,000 rows per second, maybe 10,000 rows or 20,000 rows per second, very high heavy writes. So if this is a non-partition table, then what happens? You have the B tree, right? You have the B tree structure, the primary key. So let us say this is the leaf level. This is the leaf level pages. So in this page, for example, you are writing 10,000 rows per second. Server is having multiple cores, and you will be having multiple operations because you have the maxed up, right? The parallel operations. The parallel operations tries to write multiple records at the same time into the same page, the last leaf level page. Okay, because you see that here primary key is a cluster index and it is defined an identity column, and you are inserting plenty of rows. The rate at which you insert is heavy. Okay, so then you are bombarding the database, the table, by writing too many rows into the same page. Okay, then you will, then every operation, every thread will try to acquire the page lock. Okay, acquire page lock because it has to write the record into the particular page. Okay, at the same time another thread concurrently tries to write the record into the same page, because you are inserting the records sequentially, because it is defined an identity column. You are insert all the parallel processes are trying to insert the record into the same page, thereby you will see plenty of blockings. Okay, there will be a lot of blockings. You see heavy writes can be a problem to a table which has identity key column. Not only identity column, okay, any primary key which has a sequential the numbers. Primary key is a surrogated, for example, any column which has a surrogated key, okay, sequential order of numbers, then that particular table, then that particular page will have a problem. Okay, so generally you will see if ID is the whatever the primary key, it could be ID or some other name. Okay, but if that is defined on identity column, then you will see a page latch IO, EX, and all those lockings will be on that clustered index. Okay, it could be ID, okay, whatever it is. Okay, so how the table partitioning is going to help in this scenario? What you can do, you can create, instead of all the, see, you have parallel process, right? You have concurrent process because of the parallelism, massive parallelism occurring on the server, and all of them writing to the same page. Okay, so what you can do, you can split the ID column, the table, based on the partitioning key. For example, you can create another column called partition key. Okay, the partition key, so you partition this table based on the you define the clustered index. Okay, primary key cluster index. Okay, you make the primary key as a composite key with ID and primary key, these two columns combination. Then essentially what you are doing is, instead of writing all this row into one page, you will be creating 4 pages, for example. Okay, so when you write 10,000 rows, what happens? 2,000 rows will be written to this page, 2,000 rows will be written here, 2,000 rows like this. So you are distributing the load. Okay, you are distributing the load into 4 different pages, into 4 different partitions of the same table, thereby reducing the page latch on the clustered key. Okay, so you have to create as many partitions to reduce that page latch. Okay, it is not exactly 4, it may not be 5. Okay, you have to keep increasing until you don't see this page latch going on. That's what you have to do in the load testing. You have to do load test and insert the same number of rows. For example, some you see page latch when it is 10,000 rows per second. Then you do the same load test and create 4 partitions and see if you get this problem. Okay, if you are still having this problem, then bump up to 6 or 7. Then you again do a load testing, and if you don't see, just stop it. Okay, you don't want to create 9 or 11 or 15 or 25, something like that. Okay, the reason is, again, when you see partitioning, if you see, you are using table partitioning feature to help in this scenario. Okay, heavy write scenario, page to remove the page latch, but you might be introducing some other problem. Okay, because if you have a queries that is doing a table scan, okay, or range scan, whatever it is, when range queries, they will suffer if you have partition, if you have multiple partitions. Okay, for example, a bigger B tree, okay, sometimes a bigger B tree is better than many partition table. For example, it's better to do a range scan on a non-partition table compared to a partition table. Okay, so partitioning might give another kind of problems. Okay, so select queries, it might give a problem. So you have to properly test it out, just to make sure all those select queries are performing better or reasonably well. Okay, but the requirement for this table, you just want to fix this problem. So what you have to do, you have to create a partitioning key. You have to create some kind of hash key. That means if ID is this particular number, then value is 1. If ID is particular different number, the value is 2. So we have to create a hash key, hash number for every value. Okay, randomly create. For example, 1001, the hash key will be 1. 1002, hash key will be 4. 1003, you generate a hash key, partitioning hash. The value will be 6. Okay, so 1 to 9, you wanted to generate the partitioning hash key 1 to 9 based on the value that you insert. Okay, you might be inserting 1,000,001. For example, this number, what is the hash key? Is it 7 or 2 or 4 or whatever? What is that? Okay, you take that number and put it here. Okay, 1,000,001, right? This value, you write it here, 1,000,001, and you put the partition key. Okay, so this record will be written to this page. When you write 1,000,002, the partitioning key is 3. Okay, hash key. Okay, then it goes and sits in this page, right? So now you are distributing the load. So now you are writing multiple pages. So there is no contention. Contention will be less. Okay, so that's why the hash partitioning. It is not altogether a brand new thing. It is just that the way you implement to fix certain problems. Okay, so even I have given one example in this document somewhere at the end. You see that here SQL sort of hash partitioning. Yeah, I have given some notes for you to read. Certain times there will be heavy inserts. Okay, things like that. So if you go to this website, there is an example for SQL Server hash partitioning. Okay, so you can basically you create a function, partition function. Okay, so in this example I am creating 3 partitions. Okay, and after that I create a partition scheme. Now I have to create a table. You see that here I'm creating a table, a heavy insert table. Okay, and I have created the column. You see that it hash ID cast ABS divided by 4. Okay, I'm creating some random number. Okay, hash random number, and that is persisted. Okay, random number, and after that I create unique cluster index on these 2 columns, ID and hash ID. You see that here ID and hash ID. I create unique cluster index, okay, cluster index on partitioning scheme. That means I am partitioning this table based on ID and hash ID combination. These 2 column combination I am going to partition. So if I insert 10,000 records a second, 3,000 or 2,000 records, if it has 4 partitions, then 2,500 will be written to one page, and 2,500 like that, and I'll be distributing the load. I'm fixing the problem. Okay, that's it. So if you select this particular statement, you will see that it has to go through all 4 B trees instead of 1 B tree. Okay, it's because every partition, one thing you may have to understand, see here you have 4 partitions here. Okay, this is 2012, 2013, 2014, 2015. Okay, when you create a index, okay, there are 2 types of indexes: cluster index, non-cluster index. Again, there are 2 types of indexes: aligned index and non-aligned index. What is aligned index and what is non-aligned index? Basically, when you create an aligned index, that means see this partition data. Okay, every partition data has its own B tree index for the aligned index. For the non-aligned index, it's a different story. Okay, see this is a table. Okay. Clustered index. Okay, it is a partition based on create date. Then what happens? There will be a B tree index for every cluster index, right? You define a cluster index on create date. So there will be B tree structure for the clustered index. Non-clustered index, you can create a non-clustered index if you don't specify in a different file group. Okay, you just create a non-cluster index. That means the partitioning key will be automatically attached to that non-cluster index. So the non-clustered index will also, so let us say you create non-cluster index on first name. Okay, on first name, let us say orders table, right? Let us say this is orders table. Order, who create the order? Customer first name, last name will be there, right? So first name, I am creating non-clustered index. Okay, so what happens? This is a aligned index. This is a align. Okay, you see that here a B tree structure will be created for every partition. Okay, this is what is called align index. So whenever you do a query, then probably you will be doing, if you don't specify the partitioning, the key in the where class, it is going to search in all the B tree. For example, I say select star from orders table. What will happen when I say like this? It has to search in all the B trees, right? There is not one index to search. It has to go and search in all the 4 B tree structures for the data you requested, right? There is no partition elimination. So this is expensive than one big B tree index. Right, this is a very big B tree index. So let us say you didn't partition this table. Okay, this is a non-partition table. That means when you say select star from orders, that means you will be just going one big B tree index and getting the data. Maybe you can take 10 seconds to get the data. Here it will be taking 12 seconds or 13 seconds because you have to browse all, you have to navigate, right? You have to navigate all the B tree structures. Of course, you have the parallel processing now in 2008. From 2008, when you execute a query like this on a partition table, it will create multiple threads for every partition to get the data. At least better. Back in 2005, one thread for every partition. It will really take long time if you are processing multiple, if you are touching multiple partitions in 2005, SQL Server 2005. Okay, but still in 2008 it has multiple operations. Okay, parallel processing, but still it has to touch all the B tree. Okay, so what is B tree index? I didn't talk much about align index and non-align index. Okay, so when you create an index on a table, it is by default aligned if you don't specify a file group. But if you specify this file group is what? File group 12. Okay, let us say this file group is 13, file group 14, file group 15. Okay, when you create index, you specify create index name on this particular table and brackets whatever the column names on file group, right? If this file group is for example you specify primary when creating non-cluster index, that means you are creating non-aligned index. That means you are putting the B tree. That means this for example you create a last name index, non-cluster index. Okay, but you specify different file group. Okay, then that index, non-cluster index, will be created on primary file group. A very big B tree structure, non-clustered B tree structure will be created on the primary file group. Okay, that is non-aligned index. If you create non-aligned index, you cannot do switch in, switch out. You cannot do split or merge. Okay, you have to drop all the non-aligned index before you split or merge. Okay, that is one requirement. Okay, but sometimes it's better to have one B tree structure to search. Okay, it's faster compared to 4-5 non-aligned index. Okay, in that case you create a non-aligned index, but having non-aligned index, it defeats the table partitioning actual core functionality. Table partitioning mainly, you use that for switch in switch out, switch in switch out the data, that unload load the data. That is not possible if you have a non-aligned index. Okay, so if you are successfully eliminating the partitions in your queries, then yeah, good. Non-aligned aligned index are better. Okay, but certain times you can it's better to have aligned index, sorry, non-aligned index. Okay, it's better to have non-aligned index. It's better to have one B-tree structure to search better in your for your queries. Then in that case you have to lose other functionalities of table partition, other features of table partitioning. Okay, so sometimes you may have to create align and non-align, things like that. So there is something called storage aligned index. There is a aligned index, sorry, 1 second. We have non-aligned, align, storage align. So what is this? These two are aligned, at least they are aligned. Okay, there are two types of aligned: storage aligned and just aligned. What is meant by that? So you have a partition table, which is created on partition scheme 1. Okay, so you have two partition schemes. They are defined on partition function 1. So partition table created on partition scheme. When you create non-clustered index 1 on PS1, this is storage aligned. Okay, if you create non-clustered index on primary file group, a different file group, okay, in this case I'm just saying a different primary file group. Okay, this is non-aligned. Okay, if I say non-clustered index 3, I don't specify anything. Okay, I don't specify, sorry, I can specify PS2. Okay, see, PS2 still it depends on PF1, so this is aligned. Okay, so it doesn't need to be PF1 as long as, if see, PF1 has same boundary points. Okay, PF2 has same boundary points. Okay, PF1 has same boundary points. Okay, datetime function parameter and 3 boundary points. Okay, and even PF2 has 3 boundary points, datetime. You can have PS4, partition schema 4 depends on PF2. You can use partition 4 here. So still that is aligned. Okay, this is 1. So this is storage aligned. When you create non-cluster index on a different file group, okay, not on a partitioning scheme, then it is a non-aligned. That means you will be creating one big B-tree structure for that index. When you create storage aligned or just aligned, then you will be creating for every partition, the B-tree structure for every partition. That means every partition will have its own B-tree structure. Okay. So there are certain few other things. So a table, partition function. Okay, you can create partition function, partition scheme on this, on the same function. Okay, so when you create table 1, table 2, they can use the same partitioning scheme, and table 3 they can use this. Okay, table 4 again they can use this. Okay, so it's like that. You can have same partition function, you can use it for multiple tables. Okay, all right, let's look into some other things. All right, so now let's take a look at some of the queries. Okay, all right, now let's insert few rows. Okay, now you see that I have records for partition 1, 2, 3, 4. I have some records for partition 1 and some records for partition 2, 3, 4. Okay, now let's see. I'm going to include the actual execution plan. Okay, so if I say select star from orders right, you will see there is a partition true. You see that here there is a partition true and actual partition count 1. Now if I say select star from orders right, where create date greater than 13, okay, so I execute this query. Now you see how many number of partitions it touched. You can see that, yeah, this query is doing a clustered seek and it is partition, and actual partition count is 2 because it is touching 2 partitions. Okay, it is showing it is going to touch the 2 partitions. You can see all those things. Same thing you can see partition here. Okay, so that way you can say how many partitions it is touching. So if you say like this, it's going to touch 3 partitions because less than 2014, right? Less than 2014 means 3, 2, 1, 3 partitions you are touching. Okay, so that way you can eliminate the partitions. Okay, so there is one another little thing I just wanted to cover. You see that here date time. So date time, it is a 3-second accuracy is 3 seconds. Okay, so see here 997. Okay, the millisecond 997. When you insert 998, it will round that 998 as a 997. So you have to be really careful because date time occupies 8 bytes and it has the accuracy of rounding up to 3 milliseconds. Okay, so if a record that comes for example 59999, it will be considered as January 1st. Okay, if it is 998, it will be considered as a 997. Okay, so your boundary point, you have to be really careful if you are specifying the left boundary point. Okay, so if you specify 997, 998 or 0, you know, a lot of people, many times you will see date time. Okay, so then you have to be really careful in storing 998, 998, 999 here. Okay, milliseconds, there is a rounding happens with the datetime column, datetime data type. Okay, so I hope you might have got something out of this video. So there is nothing much to talk about partitioning. At least whatever I know I have explained. There could be plenty of other things. So hope you enjoy this video. All right, thank you.